Okay, so for part 1 of homework 8-2 here, let's pick up question 1. So, a restoring force of magnitude F acts on a system with a displacement x. In which of the following cases will the system undergo simple harmonic motion? And the key concept here is obviously the fact that simple harmonic motion happens, for instance, in like a spring situation, when the force is directly related, it's directly proportional to the displacement. So, in other words, if the displacement were to double, the force would double as well. So what that symbol, that odd-looking symbol right there is representing is it is representing proportional. It's representing proportionality. So in which of these cases, again, the only time that this will happen is when the force is directly proportional to just the displacement. So no square roots of the displacement, no sine functions of the displacement, no displacement squared, and no inverses of the displacement. It is just when it is proportional to the displacement itself. So option D is the best option for us here. It only happens when it's a result of the displacement and nothing altered there. So anyway, question 1, a good one to make sure you're comfortable with for the basics of simple harmonic motion. Question 2, I'm sure, is a question that most of you guys feel very comfortable with at this point, right? When is the speed the greatest? When the magnitude of the acceleration is maximum? That's not true. When the displacement is maximum, that's the same as A. When the magnitude of the acceleration is a minimum, there's my correct choice, right? It is the speed is the greatest in equilibrium position, which is when the acceleration is 0. The potential energy is maximum at the amplitudes, which again is not true, and the kinetic energy is obviously directly related to speed, so that definitely can't be a minimum with the speed being at its maximum. That doesn't make a whole lot of sense. So anyway, question 2, probably most of us got that pretty easy. Question 3, if we double only the amplitude of the vibrating mass spring system, the mechanical energy of the system will do which of the following? And the key here is the total mechanical energy is both potential and kinetic. But again, the easiest way to find it is to find the maximum potential energy that we start with. Because however much potential energy we start with, right, when the system starts oscillating back and forth, that's going to be my total mechanical energy of the system the whole way throughout. Right, so my maximum potential energy equals 1/2 k times a squared. So if all of a sudden I double only the amplitude, right, nothing else changes, then the 1/2 didn't change, the k didn't change, but I'm doubling the amplitude and then squaring that, right? So I'm actually making this side of the equation 4 times bigger. So I'm going to be quadrupling, I'm going to be increasing by a factor of 4 the total energy of the system, right? The 1/2 and the k didn't change, I brought in this new factor of 4 as I squared the amplitude. So option D is the best one for question 3. I really like question 4 here as a good follow-up to question 3. So if we double only the mass of the vibrating ideal spring system, what happens to the mechanical energy? And the reason I like this question is when you think about it, because like we saw in question 3, right, we know that the total energy is based on either 1/2 kx squared, or you could find the total energy by finding the maximum kinetic energy, which is 1/2 mv squared. The problem with this is the fact that if the mass changes, right, if the mass all of a sudden doubles, we cannot assume that the velocity stays the same. And that's where the problem lies, right? If the mass were to double and the velocity were to stay the same, then this would increase by a factor of 2. But in fact, the energy stays constant. If the mass doubles, the velocity just decreases to then compensate for that. And the reason that's the case is we go right back to the original potential energy. Again, the potential energy is going to be what defines the total energy of the system. By doubling the mass, it did not have any impact on the spring constant or how far we initially compressed the mass spring system, right? So the spring constant and the position were not changed, and therefore the total energy of the system does not change. The mechanical energy of the system does not change. So option E is my correct choice. Again, this one you've got to watch out for, because if we just think about the kinetic energy, your gut's going to say, well, the mass doubled, the velocity doesn't change, so it should double. But again, we have to be careful, because as the mass increases, the velocity in fact does change, right? It would reduce to make sure that that equation stays balanced out. So be very careful on question 4. Like I said, I like this as a follow-up to question 3. I think it's a good one to make sure you can stop and think about the potential energy as being the defining factor for the mechanical energy of a spring system. Question 5 here is just kind of a basic concept understanding, right? A frictionless pendulum released from 65 degrees with the vertical will vibrate with the same frequency as if it was released at 5 degrees. Now, this would be true if the degrees were not 65 and 5, right? If it was 5 degrees and 10 degrees, then that would be a true statement, because that is kind of like what we've seen for the springs, right? Whether it's 5 degrees or whether it's 10 degrees, the spring will oscillate at the same period and therefore the same frequency. And now I shouldn't have said spring, the pendulum will oscillate at the same frequency in either of those situations. However, 65 degrees is not a small enough angle to where this fact that sine of theta is approximately theta is no longer true, right? Sine of 65 degrees is definitely not equal to that 65 degrees in terms of radians. So that is definitely not true anymore, which makes this a false statement, right? So again, be careful. It works to about up to about 10 degrees. So generally anything less than 10 degrees we would accept this to be true. So if I said 6 degrees and 8 degrees, no problem. They have the same frequency. 2 degrees and 3 degrees, no problem. They have the same frequency. 6 degrees and 20 degrees, that's where the issue lies, right? The angle gets too big. So this example is false, and again, probably most of us comfortable with that, but make sure you are comfortable with that key concept for. Okay, so question 6 is a nice one for just kind of breaking up the equation for the period of a pendulum, right? So the period of a pendulum, 2 pi times the square root of L over G, right? And in this case, they tell us that the period is staying the same, right? The period is staying constant. So on Earth, it has a period of 1 second. On the other planet, it also has a period of 1 second. So again, the period number here stays constant. It does not change. So if on the other planet we had to decrease the length of the pivot arm, right, the length of the pendulum, if that length was decreased and the period does not stay the same, what has to happen to G? Well, in order to keep this fraction balanced out, right, if I, for instance, cut the numerator in half, I'd have to cut the denominator in half as well so that the halves cancel out. Right? So in general terms then, if the length decreases, the acceleration of gravity better be slightly less as well. Right? So since we had to shorten it slightly, the acceleration of gravity on that other planet would have to be slightly less than G. So option B is my correct choice there as well. So again, a good example for breaking up the equation for a period, or for a pendulum. Question 7 is really a pretty basic example of the equation for a spring system, right? So the period of a spring system we know is 2 pi times the square root of m over k. They give us the mass of the bungee jumper in kilograms, so we've got that, and they give us the period, right? The period of the oscillations is 11.2 seconds, and they ask us to find the constant. So again, this one actually is probably too easy, right? It's just a straightforward kind of plug and chug, and make sure you know where everything goes. So just solving this equation for k, right? So substituting all those measurements in, solving for k, and we should get that k is about 17.6 newtons per meter. So our spring constant on question 7, certainly nothing too difficult, just taking advantage of the equation for a period for a spring and solving from there. Okay, so question 8, a very important question. I want to make sure everybody has stopped and tried this one. If you have not tried this on your own, if you have not struggled with it a little bit yet, make sure you do, because this is the type of question you guys need to be very comfortable with. So it's one that requires us to set up a position function and then ultimately to use it to find the acceleration. Right, so again, if you haven't genuinely tried this one yet, please don't just copy this down. It's not going to help you at all. And when you come to these questions on the test, it's just going to be rough on you. So make sure you put in some effort. But anyway, for those of you that have tried it, ready to check your answer here, let's kind of go through how we're going to set this up. So they give us a whole bunch of information, right? The mass, the spring constant, the positions, and then they're asking when it's at this position, when it's at this displacement, what the acceleration is. Well, the first thing I'm going to do is find the time that it reaches that position by using my position function. Right? So I'm going to set up a position function for this spring. So position equals the amplitude times cosine of, and inside the function I'm going to choose to work with 2 pi t and then times the time. And in this case, because it was pulled back and released from rest, right, at that time of 0, then I don't have to worry about any type of phase constant, right? I don't have to worry about any type of shift. So I'm good on that. So I've got this set up. I'm going to go ahead and calculate to solve for my period. So my period is 2 pi times the square root of m over k. My mass is 0.28 and my constant is 500. So my period is about 0.1487 seconds. Obviously you could round that off wherever, but I'm going to take it to a few decimal places and make sure I stay pretty accurate here. So then plugging into my position function, again my goal is I want to figure out how long it takes for it to reach that position. So I'm going to go ahead and plug in the negative 0.052 as my position, I know my amplitude is where I started at there. That's where it was released from. So 0.080. And then times 2 pi divided by the period, which I just found was 0.1487. And then times the time, which I don't know yet, right? Oops, I forgot my cosine in here. There we go. Okay, so the cosine of this whole mess. But anyway, solving this, so dividing both sides by 0.080 and then doing the cosine inverse of that. So I get negative 0.052 divided by 0.080, and then I'm going to do the cosine inverse, right, to get rid of the cosine function of that whole mess. And that'll leave me with just the 2 pi divided by the period, and then times the time, which is what I'm looking for. Make sure, of course, you are in radians anytime that we're using the inverse cosine or cosine function, right, for these type of equations. We need to make sure we're in radians. So if I'm in radians, I end up getting 2.278 as about the approximate value of this cosine function, and then again that equals this whole mess over here, 2 pi divided by the period, and then times t, so then I just have to solve for t. So when I solve for t, I get 0.0539 seconds. And that's how long then it takes for it to reach this position. That's how long it takes for it to reach that position for the first time. And if I look at the time, it kind of makes sense, right? It's kind of consistent with the period. We know this is a little bit more than a quarter of the period, which makes sense because it's gone from being at positive 0.08 to being in the negative displacement, right? So the spring, if I'm thinking about this as a visual here, right, the spring has gone from the positive direction, it's past equilibrium, which would be a quarter of the time, and then it's now somewhere over here, right? So that makes sense that this is a little bit more than a fourth of the period, right, in order for that to happen. So that seems like a completely reasonable number for me, but it is good to be thinking about that as you guys go through this problem. But anyway, so I've got my time. So then how can I use that to help me with the acceleration? Well, the key is, again, I'm going to set up my acceleration function. And you actually could just set up your position function and do the second derivative of that, and there's nothing wrong with doing that. That actually, maybe for some of us, is the easier route to get there. And so again, if that's what you're comfortable with, do that. You should end up getting about the same answer I'm about to. But what I'm going to do is I'm going to go ahead and just kind of jump in with this equation. So I know my acceleration at any instant time equals the maximum acceleration times the, or negative the maximum acceleration times the cosine of this whole function here. I just found the time that it takes me to reach that position. So that was the whole point of finding the time, is I can substitute that time in. So then the only variable I have left to solve for is my maximum acceleration. Excuse me. So to find my maximum acceleration, I'm actually just going to take advantage of force equals the spring, right? Force equals Ka. So the maximum force equals K times the amplitude. So then if force is mass times acceleration, if I break this up, right, it'd be Ka divided by m. So my maximum acceleration, and the reason I'm choosing this route is because they gave me all of those measurements. They gave me the spring constant of 500, they gave me the amplitude of 0.08, and they gave me the mass of 0.28, right, so 0.28. So they gave me all of those measurements to work with, so I might as well just take advantage of them and use them to find the acceleration pretty quickly. So 142.86 is what I end up getting from my maximum acceleration, and I'm going to substitute that in over here. Right, so I've got my time from using the position function, I've got my acceleration by either doing the second derivative or by just calculating it using the numbers they gave me, and then substituting all of this in, right, so negative 142.86, and notice I do keep the negative in there, and then cosine of 2 pi divided by the period of 0.1487, and then times the time that I found up above, right, so the time from before, which was about 0.0539, and then calculating this whole thing. Once again, make sure you are in radians in order to do this, and if I'm in radians, I get about 92.8 meters per second squared. Okay, so about 92.8 meters per second squared is the acceleration at that instant in time, right? So it's at that position because that was the time that I found, and so at that instant in time, at that location, it's got an acceleration of 92.8 meters per second squared. Okay, so I definitely will stop the first part of the video on this question. Again, guys, question 8 here is a very good one. It's a pretty standard question that they would expect us to be able to tackle. So if you do have any trouble with this, if you do have any further questions on this, don't hesitate to let me know, because this is definitely the type of question you'll see on your tests and quizzes.